Okay, I can see this recording start. Okay, today I'm going to introduce Rasch model to you. It's actually a simple model, but it is also a different model from other psychometric model we have learned. When I think about the title for today, there are many titles. So, but I determined to use this one, May Item Fit. This is actually represent an important philosophy difference of Rasch model from the other model. But before I introduce Rasch model, let's go over some typical process of measurement development. We start with a concept, a standard, or some outcome we want to measure. And then we decide the items to reflect the concept. The next step is field testing. We'll conduct psychometric analysis with the resources from the field testing and evaluate the item quality of it. Oftentimes, we need to revise our original item. So this is a general process of measurement development. And during this process, items are the basic unit of measurement. So in every measurement, there are many items. On the right-hand side, you can see an algebra item from SAT. It requires students to solve this equation to get the the value of R and X. So items are designed to collect evidence of the concept to be measured. They are designed for certain purpose. They also differ in their characteristics, such as item difficulty. And this is why we're running so many psychometric analyses. We want to find out what their characteristics are in a quantitative way. And item difficulty, discrimination, and guessing parameter are very important characteristics of those items. And item response theory is one of the most psychometric theory in our field. It decomposes responses into respondent traits and item characteristics. In terms of item characteristics, there are many parameters, but difficulty, discrimination, and guessing are the three most popular parameters in IRT analysis. And depending on the number of item parameters we have, there are 1, 2, 3 parameter IRT model. On the right-hand side, you can see a 3P arrow. We have A as the discrimination, describe the steepness of the curve. We have the B as the difficulty parameter that determine the location of the curve, while C as the guessing parameter determine the lower limit of our parameter of our curve. So this is the IRT model, and this is the equation for it. Building from 1P arrow, we only have one item parameter difficulty. Then we have two parameter logistic model with discrimination and difficulty as the two item parameter. And then we can move on to 3P arrow. There are 3 parameter guessing, as denoted by C, A discrimination parameter, and B difficulty parameter. So when we're talking about different RT model, you use number, and actually those numbers refer to the number of item parameters. But in terms of the reality, when we decide our item and collect the responses, our observation does not always fit into the curve we want to try to fit. For example, this is a Rasch model in a red curve, and we also have our observation in a blue dash curve. You can see there's some deviance between our expectation, the red curve, and our reality. This is our observation, empirical evidence, empirical responses in blue dash curve. So that deviance. And this is the 2-parameter RT model, 3-parameter RT model. You can see our items are not always perfect. Therefore, there are always some misfit between our observation and the expectation. So how to make our item fit? There are 2 strategies. The first strategy is like, okay, now our item, our data doesn't fit into the model. And then we need to increase the complexity of our model to fit the item. For example, if a single discrimination parameter cannot describe all of the item, therefore we need to use two parameter RT model. If there's a guessing we cannot accommodate, we cannot address in the items, and then we need to add a guessing parameter. Of course, we can also further increase the complexity of our RT model to 4p error, 5p error, maybe even more. So this is one way to address the misfit between items and our model. The second is actually revise the items to fit the RT model. For example, we start with the 1p error, and we observe some deviance. Maybe for this item, is at the higher ends of theta. Then we need to control this path. We need to control some of the item property to make this part of responses more aligned with the expectation, which is the record. These two strategies actually reflect different pre-assumption. The first strategy, increasing the complexity of RT model. As you can see, we have this is observation. When we use first 1PR with 1PR model, we find that there is like an underestimate of our observation. And 2PR, if it's better, and 3PR, it doesn't fit better. Maybe we can choose 2PR. This is actually a very often used strategies in reality, because in industry or in many cases, item development is expensive. Especially, we need to have multiple rounds of field testing and item writing and revisions. So therefore, in many industry, they tend to increase the complexity of RT model to fit the items. But with this, and moreover, some of the item property are inevitable, such as maybe guessing in certain item, you cannot get rid of it. But there's assumption underlying this strategy. When we want to increasing the complexity of our item model to fit items, it means that we believe our items collect among our model is wrong. Therefore, we need to change our model, make it more complex, and revise our model to fit the items. This is the first strategy, the assumption underlying first strategy. However, today, let's focus on the second strategy. How about our items are wrong, but our RT model are correct? So in these cases, our assumption. So in these cases, our assumption is that RT model are correct because model are just model. They try to model the complexity of our work. But our item, as is decided by human, may be subject to different kinds of errors. And we need to revise that so it can better fit with the model. And under this strategy, instead of increasing the complexity of the model, we should focus more on the items, like how we can design an item that fit the model, instead of finding a model that fit the items. And this is the logic of Rasch model. Am I right to bring in this metaphor? For acknowledgement, this image is created by GPT, and this metaphor has come from my doctoral advisor. Okay, now let me introduce the metaphor. Building an instrument, a measure, questionnaire, or scalar is like building a bridge, a wooden bridge. So before we building the bridge, we have a blueprint in our mind, and then this is like the bridge we want to build. And each wood is actually an item. When building this bridge, and we need to search for different woods, and we need to compare those woods with our blueprint. And in these cases, the blueprint is the Rasch model. So we cannot simply go into our forest and find a random wood and build our bridge and change our blueprint. So this is not the way we build a measure under the Rasch model. The Rasch model tells us this is how a good item should look like. And we need to decide the item that fit the model instead of bringing any random items and make our measurement. So this is the key idea underlying the Rasch model. And now let me introduce Rasch model. As you can see, this is actually a similar equation as you can see in 1P error, because in terms of Rasch model, in terms of the number of parameter, there's also one parameter, but there's some mathematical difference between Rasch model and 1P error. In 1P error, we still estimate one discrimination parameter. So one discrimination for all, but for Rasch model, the discrimination method can be set to 1. In addition to that, the equation will look similar. Under this formulation, items only differ from each other in terms of the difficulty. Now let's take a look at the plot on the right-hand side. As we know, item difficulty is it's the corresponding theta when the probability is equal to 0.5. And I highlight it with a red dashed line. So in this plot, we have 5 items: red, brown, green, blue, and purple. They only differ in the difficulty. So if we have for this red plot, you can see the intersection between the dashed line and the curve. It is whose x is corresponding to, let's just say, maybe negative 2.5. So this is the difficulty of the red item, negative 0.25, and this is the brown one, maybe it's negative 1, and the green around 0, and this is around the blue one around 1, and the purple around 2. So this is only one parameter of the Rasch model. And why do I need to mention that? Always mention this particularly, because it leads to one important property of Rasch model. To talk about that, let's compare Rasch model with 2P error. Now, let me draw another line. For example, we have a respondent with latent rate, or let's just say it's about -2. I need to make this line bigger. 2. And as you can see, for this respondent, let's call it respondent A. His ability, in his mind, the red item is always more easy than the brown one, then the blue one, then the green one, blue one, and finally the purple one. The purple one is always difficulty. And then, what if we have another respondent? Let's call it respondent B. And I use different color for this respondent. In his mind, the red item is difficult to brown, and then the green, blue, and purple. So from these 2 students, you can find that no matter for which respondent, the order of item difficulty remain the same. We can move this vertical line to any place. The order of difficulty will not change depending on the theta, on the latent rate. But this is not the case for 2P error and also for the other model. For example, let's place -2, not the brown, for respondent A in the 2P error. We find that the green item is more difficulty than the brown, than the orange item, and then the red item. But now, what if we have a respondent B? He's at let's say he's at negative around 1. So in these cases, something changed. Yes. The orange item become the most difficult item, and then the purple item become the second to the most difficult item. Therefore, under 2P error, or in model that's not Rasch model or Rasch family model, the difficulty of item change. The order of item difficulty change depending on the location of the latent rate. So this is create a problem As we know, if we believe item difficulty, it is inherent, it's a characteristic of item. Therefore, its interpretation should not change depending on the persons. But this is one of the issue with the 2P error. And why this is important? Because in building a measurement, in lots of our measurement, our constructs are latent. Latent means that we cannot observe it directly. So we need to build a lot of evidence to make our measurement trustworthy to our audience. And trustworthiness can consist of two aspects: objectivity and subject independence. For this, for today's presentation, let's focus on subject independence. It refers to the goal that the conveyed information will be interpreted in the same way by different persons in different places and times. But if you are using 2P error and it change, depending on the location of the latent state, different people will have different interpretation of the item difficulty. For respondent A, represented in the orange vertical line, you find that the brown item he has a higher probability to answer the blue item correctly, and then has second to the best probability to answer the orange item correctly. But for the respondent B, it changed, become become orange, and let's just call it brown, or let's call it orange, and then blue. So they change. The interpretation of item order change depending on the location. And this will pose threat to the subject independence, and further pose threat to the trustworthiness of the measurement. And this is one of the benefits of Rasch model, because at least from the different trade level, we can ensure that the item difficulty will not change. The item difficulty order will not change depending on the filter level. So this is reflect the philosophy of Rasch model. So this is the quotation from the Rasch. It means it tells us the comparison between two items should be independent of which in particular individuals were instrumental for comparison. This is what the example I just mentioned before. The comparison, the difficulty, let's say the difficulty of any two items, the relationship will not change. It will not change because of different latent trait. And from the person perspective, a comparison between two individuals should be independent of the particular items within the classes considered were instrumental for the comparison. So the comparison of items should not change based on what item you are using. This is what Rasch model trying to convey. But now let's focus on two aspects. Right, in the Rasch model, when there's a misfit between item and the model, we need to revise our model. And the Rasch model also enable inter-subject independence in terms of the latent trait level. This is the insight of Rasch model can provide us in designing measures. And we can also collect information from both latent trait and item difficulty together. And this is one of the most important products of Rasch model. It is called RightMax. RightMax is developed by so this is a last name of a developer. It places the latent trait and item difficulty together. On the left-hand side, you can see the distribution of the latent trait. You can see this is actual histogram, and we have like our respondent with low a low ability to high ability. On the right-hand side, you can see the item difficulty, which is item difficulty for each of the X represent one item. So we have easy item to difficult item. So this and this visualization actually is the result of our model theta on the left-hand side as the latent rate, D as item difficulty on the right-hand side. We place together. This is only possible under the Rasch family model because in 2PL, the difficulty and the latent rate might not on the same scale. So under this right map, they are on the same scale. It enables us to examine the alignment of respondent and items. So in this right map, you can see they are actually pretty matched, but they are more easier. The items are more easier than our target population. We can compare them together. And moreover, the Rasch model can help us in item design. You know, when we are designing a measure for a certain population, there usually be a wide range of our respondent latent rate distribution. And this is the purpose we want to, and can be one of the motivation we decide the measure. There's a wide distribution. We want to assess the distribution of individual respondents latent rate precisely. Therefore, we start to design an item. And an item can provide most information for the respondent whose latent rate level equal to the item difficulty. For example, we have two items here, the blue item and the red item. They differ in their difficulty, as the red item are more difficulty and more difficult than the blue item. And this is the information curve. It's based on the Rasch model, and you can see the peak of the information can be achieved when the respondent's latent rate is equal to the difficulty. For the blue item, its difficulty is -1, and therefore we can have more information about this item or provide more information to the respondent whose latent rate is -1. And for the red one, it is the difficult item whose difficulty level is 1.5. And we have the most information for the respondent at 1.5 at the theta of 1.5. So this is the information curve. Well, in designing our item, so we can change two things, right? If we only have our respondent around 1 and 1.5, we have the most information for them. But actually, when we're designing our measurement, we cannot decide. Usually, it means that we cannot decide our population. Therefore, it means that we cannot only select those respondents in the reality or in administration. But there's a different story in computer, like adaptive testing. For now, let's focus on the traditional measurement. But on the other hand, how about we decide the item that fit our population? So we have this, for example, if we have a dense population population at around theta of 0, maybe we can design more items around this level, so we can provide more information about our population. And in the Rasch model, under the Rasch model, we can better decide it. First, we can start with identifying some qualitatively different level in the population. This is our right map. On the right-hand side, you can see the population trait. Of course, we don't have those information before we decide. This is actually after the field testing, maybe also after the formal administration. But before that, we might have a hypothesis, a theory about population. I would like to use the argumentation as example. So in order to form an argumentation, we need to have claim and evidence, and then we will form an arguments. And finally, at the highest level, our respondents should be able to create content critique or comparative argument. It represents a even higher level of argumentation skills. So based on our observation, in my content 4 level 0, we don't have the respondents should possess nothing, know nothing about argumentation. Moving up, they start to be able to identify claims and evidence, and then they can complete an argument based on the claims and evidence. Finally, based on the complete argument, they should be able to provide comparative argument. So this, in our theory, there might be 4 levels of our population, from the lowest to the highest, and then theoretically there should be different minimum. So different, we can separate our population, or maybe we can insert a vertical bar in our population that reflect different level of our respondent. For example, under the orange one, maybe they represent nothing, no knowledge about argumentation. And then between the blue and orange, claims and evidence, and complete argument between the red and blue, and finally about the black, we have the highest level. So we have maybe after some theory building might have 4, and then we can decide our item to assess different level of it. Different level of it to better reflect the different characteristic of different level. So this is actually, to me, is an advancement to other method. If we don't have those level, we need to decide an item that assess. We don't know when we decide item. We don't know which level we are deciding. If we want to use one dichotomous item to assess all of this level, all the population, it will be much difficult. No, and dichotomous item is very limited by the difficulty. But with those different level, we can better decide it. And one more benefit of it is actually, after that, with this method, we can use our line map to provide more structural validity evidence to our measurement. Suppose now we have decided 3 levels of item, level 1, level 2, and level 3. And then, if our items are developed properly and aligned with our expectation, we will observe a cut point between level 1 item and level 2 item, level 2 item and level 3 item. And it will provide and construct validity and structural validity evidence to your measure and decide. So the cut point is actually supported by a claim here, qualitatively different level. And this qualitatively different level is determined by your theory, expectation, and expertise. If you don't observe that, so this if you don't observe that, it means that your idea of those level might be wrong, or your item might fail to capture this level and to revise it. And this is the 4 building block approach that I just mentioned. We start from a concept map. A concept map means that it's a concept to be measured, such as the argumentation. And it's this step, we also need to decide some of the waypoint, determine some of the waypoint. Waypoint means some qualitatively different level. And in this plot, it's like the orange, blue, and red. So this is for visualization, but in reality, we only have like some text or some description of each level itself, like this vertical bar. And then we move on to decide item. We need to decide item instead of reflecting the whole range of this fit of this latent rate. We focus on decide item that are on different level, that reflect different level of the target of the construct of the measure, and then we convert responses and draw the line map to verify its structural validity. If it doesn't satisfy, if you find there's a lot of chaos in this line map, maybe some of the blue item, level item are too difficult and they jump to maybe 0.1, and some of the orange item are some of the orange item fell below maybe negative 0.1. That is common because it's especially in the initial round of development, and it means that either our contract, the level we define is long, or the item is long. And under this alignment, we can, under this paradigm, we can translate it differently. And this is actually from this book, and this is an so it is about construct methods and item response theory modeling, and it is written by my doctoral advisor, Mark Wilson. You should be, as a UNCC student, I think you also have access to its online version. If you are interested in this development paradigm, you can read it. And actually, some of the content from my presentation is also come from this book. So this is a four building block approach in design management, and this approach is only applicable when we are using the Rasch model. And moreover, let's move on. Move beyond the right map. And the Rasch, one more benefit of the Rasch model is can provide more information for item revision. That's the fact that our initial design item is not always perfect. There are always some problems. That's why there's a multiple revision, multiple round of field testing in order to find out, in order to determine the final risk of our item. So we always need to revise our item. And for item revision, we need some information. We cannot randomly revise our item. There must be some revision statistic we need to use for item revision. And item fit statistic can provide part of it. And item fit statistics for the Rasch model can provide more information. And this is how we can calculate it. First, we have this Rasch model. Based on the Rasch model, we can calculate the expected score, which is the probability, because this is binary score. And then we can calculate the variance based on the model, and because this is a binary responses, the expectation, the variance is about is the product of successful rate and failure rate. And then we can calculate the residual. It's the difference between our observed score and the probability. You need to standardize it with the variance. And with that, we have all of the information we need to calculate the fit statistic. And we have for item, because we are revising our item, therefore we need to aggregate the fit, the deviance for every item. So our fit, so we have like, so the most straightforward way is just to average all of the deviance for our respondent. Suppose we have n respondents, and then we have n deviance. We just need to calculate the standardized deviance, and we will find the outlier sensitive fit. Why this is outlier sensitive fit? Because for those respondents remain in the middle, our prediction of the probability might be you have 0.6 probability of successfully answer this item. And if it answers this long, it's just the penalty is only 0.4, right? For those in the middle, or for those in the middle, it doesn't influence the fit statistics too much. However, for those at 2n, they are called sometimes they call outliers. So they call outliers like those from around -3 and those around 3. And if there's one long prediction, it will have high influence on the fit statistic, because for those respondents, for example, for -3, usually for many of the items, the probability for them to successfully answer an item can be just 0.1. However, if he or she accidentally answers this item correct, the deviance is 0.9. So it's the case for for 3. So for example, we have main item that predicts its probability, and they should have 90% of probability to answer this item correctly. However, accidentally they answer this item incorrectly, and there will be a 0.9 in the outliers, in the misfit. So this will make the item fit statistic very sensitive at the 2x, and we can have another fit that we call infit. Remember what I had mentioned before, an item can provide more information for the people whose ability or latent rate that is close to the item difficulty. And in these cases, we will place more focus on those respondents. So to assess the item fitness, we will, with the infit, it will weight more by those respondents whose latent rate are close to the item difficulty, because they can provide more information. And this is more often used in item development and revision. We use infit a lot, and this is called inlier pattern sensitive fit. And there's a critical value for these two statistics. And if you are using a more linear way, and you can use 1.5 and 0.5. And any item between 0.5 and 1.5 can be considered as fit item. But those items fell below or fell above 1.5, it means that there are too many noise in your item. Your item as a window to capture the evidence of latent rate is failing, because the responses we collect for this item contain too much noise, and there's not much signal to capture the latent rate. While it is below 0.5 and the data is too predictive, so they are too predictable, it doesn't provide enough variance to reflect the item, to reflect the latent rate. So this is actually kind of often happen when items are redundant or Gutterman-like item. So for Gutterman style of item, and this is another topic. So we get used to the Likert scalar item, from total discrete to total agree, from not very often to always. So this is a Likert scalar item, but there's another family of format, what we call Gutterman scalar item, and this will be another topic. So with the Rasch, under the Rasch model, we can calculate the infit and outfit, and then based on the infit and outfit statistic, we can revise our item, whether this item is too noisy or whether this item is too predictable. And moreover, this table can also make the interpretation this is more straightforward. So we have many items. In terms of the difficulty, the right hand side is more difficult, while the right hand side is more easy. It's more difficult. So you can see there are lots of collectiveness on the left hand side, while there's lots of zero on the right hand side because it's more difficult. This is ideal because this is a watch-tried model, and under this pattern, you will find an outfit of 1 and an infit of 1 as well. This is the perfect item. However, if it is too predictive, you can find that after one statistic item, 1 point, they're always 0, and below those points, and always 1, it's too predictable. And what are reflected in alpha and infit is they're very small. They're below 0.5, and this is around 0.5. So they're too predictive, too deterministic. And they can be miscoded. For example, in the middle, there's a miscoding. So this should be 1 and this should be 0. There's a miscoding, maybe miscode, and you will find a large outfit and a large infit. And there are also other patterns. Sometimes we can rely on this table to make interpretation of the fit statistic. If you are using 2p error or 3p error, you can have different item fit statistics, such as root mean square deviance. However, those statistics cannot provide as much as interpretation as Rasch model. And those infit and outfit in the Rasch model are more useful when you want to make interpretation of item fitness. And if you want more information about this statistic, you can go to rasch.org. And this is an important website for the Rasch family model. And finally, to the end of our Rasch model. And actually, I mentioned Rasch family model a lot in this presentation. It means that Rasch model is only part of the Rasch family model, because it only deals with dichotomous score, means that we only have 0, 1, 0, 1. But there can be more than 2 categories, such as polytomous score. In polytomous score, under the Rasch family model, we have rating scalar model and partial credit model. They are common in deal with the polytomous case, but they differ in terms of the difficulty. We have 2 plots here, 2 diagrams here. on the top one, you can see this is a rating scalar. This is reflect the difficulty for rating scalar model. So this is the step difficulty. And there are two items, orange item orange, and blue item. What you can observe is that these two items only differ in terms of the mean location. The orange item is more difficulty than the blue one. However, in terms of the step deviation, for example, we have like 5 categories from strongly disagree to strongly agree. And the difference between the strongly disagree to disagree is for orange item is the same for the blue item. Likewise, you can see the second deviation is also the same across item. And what it is reflect in this equation is you can see is it separates the step difficulty into two parameters. Bi, the average item difficulty, and tau j, the step deviation or step threshold. And you can see there's no subscript, item subscript for the tau, step difficulty here, step threshold. And because it's remain the same across item. And in terms of the partial credit model, if I write that in this way, in the rating scale way, there should be an item subscript for the step deviation. So this is the difference between Rasch family model and in terms of the Pareto score. Moreover, there are also other useful extension of the Rasch model, and this is a table that describes the explanatory explanation. If you go back to Rasch model, you can see we have two parameters, latent rate. We have latent rate and item difficulty. So we can further decompose this latent rate effect and item parameter in an explanatory way. For example, we want to see whether there's a substantial gender difference in terms of argumentation. As we know, argumentation is the latent rate, and we can incorporate gender as a predictor on the person side. And this will make a person explanatory model. And of course, sometimes we want to explain the item difficulty. Suppose we have many items, and some of the items contain a picture. You need to use a picture to help students understand the scenario. And for those, we can also incorporate an item predictor on the item side. And this make item explanatory model. Of course, if there's nothing about the item predictor or person predictor, this becomes the model we just see. This is what we call double descriptive model. We only describe the latent rate of person and the item difficulty of item. And if we have both predictor, this is called double explanatory RT model. We explain both latent rate and item difficulty. So this is the extension of it. And we still have around 10 minutes left. Any question?
Thank you so much, Dr. Sheikh. We have one question in the chat.
Okay,
it's
let me take a look at it.
Donator.
Okay, and we can run us from Donator to the type of test construct inference. Okay, so this is actually a good question. If you can take a look at the chatbot, and Donovan is asking whether the test construct can influence what is suitable in terms of the model choice. And I think yes, I think it's possible. So you can decide your construct, but generally, when you start to decide an item, you should also reflect on what is a good item in your theory. So what is a good item for your construct, and how a good item should look like. So therefore, even though you can consider the influence of test construct, but the core in this case is actually about item, how the item fit the construct, and whether a rational or binary item or some simple item can capture the concept. Oh, Henry, that's a good question. Yes, in a lot of test company, they still use the Rasch model, and I work for some company, and they're different reasons. They still use the Rasch model. There are many reasons. First, they want to increase the interpretability. You know, when you have a Rasch model, you can, as you can see, you can set the standard setting is more straightforward. You can definitely decide the item. That reflect the level. Second, compared with 2PL and 3PL, Rasch model require a small number of respondents. I believe it's like 50 to 100 is sufficient for a Rasch model, but for 2PL, 3PL, it's more difficult, especially for 3PL, because you want to estimate the guessing pattern. The pattern have some student at the lower end of the latent rate. Moreover, Rasch model is make us easy to communicate with our audience. One thing I don't is mentioned in this presentation is the latent the total score is the sufficient statistic of latent rate. For latent rate is a better estimate. What does that mean? So if we draw a line with a calculate correlation between the observed score and the latent rate, it should be perfectly correct, like close to 1. So this helps us to communicate with our parents or our audience. So sometimes they will tell us why my child have the equal number of correct responses as his peer, but he get poor score if you use 2-arrow or 3-arrow. But under the Rasch model, we still can maintain this relationship. And there are also other reasons. If you transfer from classical test theory model, you can find Rasch model is more easy to acceptable. So there's a reason. First, in terms of the parameter, and the one, so we are requesting we can use fewer number of students in the field test. Second, for the interpretation, it's much easier. Moreover, it is also easy to it can provide more information for item revision, so we can know why an item is long. Moreover, it's a long tradition, and this is a very large community of Rasch model, and where they can find a lot of support. Okay, this is a question from Mark. What are the implications of MLE? Oh, okay. I'm so glad you mentioned the different estimation method. We are joint maximum likelihood estimation, condition maximum likelihood estimation, and WLE. So CMLE is only applicable in the Rasch model because it make use of the sufficient statistic I just mentioned. And for JMLE, its joint maximum likelihood is for treat both item and person. Let's go back to our right map. This is our right map. We have the latent rate, we have item difficulty. And item difficulty are generally modeled as fixed effect. There's no for the latent rate, generally they are modeled as random effect. Random effect means that for theta, it should be subject to maybe a normal distribution or standardized normal distribution. So this is a random effect, and random effects actually, if you are using actual M, this can be a side product of it. But in RT, we care too much about it, so we had to estimate. Under the JML, it doesn't assume a distribution. It assumes that this is a fixed effect, like an item difficulty. This can be helpful when your target population is not normally distributed or you don't know the distribution, especially for some gifted children or some talented children. You know, there's peak in certain area, or for those students in special education, they're also in a certain area. It's not normally distributed, and then you might consider JMLE or CMLE. For WLE, it is very actually WLE is as a method to estimate the latent rate. But I believe what you want to mention is the MMLE, maximum likelihood estimation. And when you have that, you can calculate the latent rate with the WLE, weight likelihood estimator. Okay. Does that answer the question, Mark?
Yes, thank you.
Any more question? All right, great. And okay. Okay,
thank you very much, Dr. Shea. Yes. I said thank you very much, Dr. Shea, for this wonderful presentation. Really appreciate it. And this has also revived our memory on what we've learned previously. So I'm sure a lot of people got a lot from this presentation. This is the last session for this is the last session for this semester. So I want to thank you guys, everyone that has stayed with us since we started till now. It's been a ride, and we've got a lot of amazing people. And I want to assure you that next semester will even be better. We'll get more people, and you might even see people that you've seen before come again just to teach us on some more interesting stuff. So I would like to wrap it up there. Does anyone want to say anything before we close? All right, thank you. Okay. You want to say something?
So thank you for attending this presentation. And actually, one thing, if you forget anything about all of my slides today, but one thing I want to keep in mind, Rasch model, even though it's a simple model, it has different philosophy than the other model. So, and sometimes if you are a Rasch family model community, if you tell them Rasch model is 1PL model, they will be mad because the philosophy is different and there's a little bit mathematical difference. But on the other hand, I wish you a success in the measurement. If you are interested in more about developing items in the Rasch model or under the Rasch family model, feel free to contact me. And wish good luck and a wonderful summer break.
All right. Thank you so much. Thank you, everyone.
Thank you, Dr. Shura, and thank you, everyone. It's been a great lecture series, and I look forward to next semester.
Thank you, everyone.
Bye.
Bye, everyone, and thank you.